Hey, AP Calc students, welcome to another live stream. This is Mr. Rich. I'm going to go over today limits, and we're going to do limits using analytical methods. So I appreciate you joining me. I am a teacher here in Jacksonville, Florida at Stanton College Prep. Hopefully some of my students are watching. We started class this week. I don't know if you're watching this, if your AP Calc class has already started, but ours started last week. And so we are in the middle of looking at limits. That's the topic of this week. So what I'm going to do is I'm going to cover some ways that we can analyze limits analytically. And the methods that we are going to go over is, number one, we're going to talk about how to do direct substitution. So evaluating a limit by actually substituting the x value at which we're evaluating the limit. And then we're going to go over another method where we may have to factor and then simplify and then try to resubstitute back into the function. After that, I'm going to show you the conjugate method and how to evaluate when that's warranted. I'm also going to show you some special trig limits. So I'm going to show you when you're dealing with some trig functions that we can use one trig limit that we have learned, at least in our class, and how to do that through some substitution. Not going to show you L'Hopital's rule. That's another method that we can use for evaluating limits, but we have to know how to take a derivative first. So that'll be coming in a future episode. And then the last one, as a bonus, I'm going to show you how to do one-sided limits. I hope I have time for all of this. If not, though, that one might have to slide, but I'm going to try to fit that one in as well. Okay, so let's start, first of all, with direct substitution. So what I'm going to do is I'm going to share my screen and show you some problems and just talk through some examples and show you the concepts, and you should get the hang of it. A lot of you have taken pre-calculus, and so you've seen direct substitution. You did a lot of that and probably have worked with some of these methods, at least to some degree. So what I'm going to do is share my screen. So give me a second to get that set up. And let's see, share screen. Let's do it. So I think we are going to do it this way. So the very first thing is direct substitution. So there we go. Set those to the side. All right. Okay, so here we go. So direct substitution. So I've got this limit here. And really, when we're doing limits without the benefit of a graph of the function or a table of values, then we are going to just do this analytically. And our very, very first step is going to be to plug in the x value into the function that we're evaluating the limit at. So I'm going to do this and say, okay, well, let's try this and see what happens when we plug in e for x. So I get the natural log of e over 3 times e. And this requires us to know how to handle this natural log of e, right? It is equal to 1. The natural log of e is 1. So my answer is 1 over 3 times e. And I would leave it just like that. If this was a multiple choice problem on an AP exam, that would be the answer that you would see. Now, it's worth mentioning, why is the natural log of e 1? And that's because natural log is log base e. And therefore, I am taking log base e of e to the first power. And one of the properties of logarithms is if you have a match here between the base of your logarithm and the base of the argument of your logarithm, they cancel each other out. And your answer here is just the exponent. All right, so that's the first one that involves direct substitution. All right, I picked both of these here because they involve logarithms and they require you to use some knowledge of logs to get to an ultimate final simplified answer. But again, I'm going to try direct substitution. I'm going to go ahead and plug in my value of x where I'm evaluating this limit at, and that's going to give me log base 3 of 9. All right, and so you want to be able to do that without a calculator. If you have a TI-84 or any other similar scientific calculator, you can put in any base of logarithm that you want, but you really don't want to have to do that, right? This right here, I'm going to rewrite this as log base 3 of 3 squared, right? And again, so I'm using that same property. I've got a base of my logarithm matching the base of the exponential in my logarithm. And so in a sense, they quote unquote cancel each other out. Logs and exponentials are inverse functions. So if I take the log of an exponential and the bases are matching, then I'm going to get an answer here of 2. So that is my answer. Now, it's worth mentioning this to you, right, class? If you're working these problems and you're trying to make sense of all this, it makes sense for you to graph that function, log base 3 of x plus 4, using something like Desmos, and look to see, what is happening there at x equals 5, is the limit 2. But, when you take a look at this function, let's just graph it or sketch what the graph would be. Right? What we're saying here is this function, if I were to graph it, I know that this is a logarithm function that's shifted left by 4. Right? So it's coming over here with a vertical asymptote at -4 because of a horizontal shift. What that means is this function, I know what this function looks like. Right? It's going to look something like this. And what does that matter? Well, it matters because I know that that function is continuous. It's got no discontinuities, and 5 is in the domain of this function right here that I have just graphed. So if it's continuous and 5 is in its domain, then that means that the limit has to exist, and the limit would be the value of the function at that particular x value, right? So over here at 5, this thing's crossing at x equals 4. So it's coming up like this, or actually 2. Right? Our answer here is 2. So it's coming up to a 2. So it's kind of making a sharper curve here, and coming up here and coming up through y equals 2. So my point here is this, to make sense out of things that you do in calculus, be sure that you make connections between analytical work and graphical work, because you're going to be working in both of those realms, those domains. So make sure that one makes sense with the other. Let's do another direct substitution. So through direct substitution here, I'm going to make this become just sine of 2 times pi over 6, which is to say sine of pi over 3. And from our knowledge of the unit circle, we know that sine of pi over 3 is root 3 over 2. So know your unit circle. And also just a plug for one of the previous videos that I did over the summer. I did a video on reviewing logs and exponentials. So if you feel like you're a little bit weak on rules of logs and properties of logs and how logs and exponentials interact with one another, definitely go back and check out that video. It was a live stream, and you'll see it on the YouTube channel. Now we want to go to the next step, right? The factor, simplify, and substitute. Because there are times when direct substitution is not going to work, and you'll see that here on this first example. But we always do start with, we always try to start with direct substitution. So let's try that and see what happens. So when I substitute the 2 in here, right, I'm going to get this, and then down here I'm going to have 2 squared. So this is a plus 2 squared minus 6 times 2 plus 8. Now, what that's going to give me is 4 plus 2 minus 6. So that does give me a 0 on the top. And down on the bottom, I'm going to get 4 minus 12 plus 8. That's 0 as well. So really what I get through direct substitution is something, it is 0 over 0. Now, one tip, your teachers will probably tell you this, right? Don't ever on a free response question set up a chain of equalities and connect your limit to 0 over 0, because that's not true, as we're about to see, right? That limit is a value, but it's not 0 over 0, right? Nothing is 0 over 0. So we don't ever want to write that and show that. The best thing to do is to do this, erase it. Right? I'm not even going to show that as a part of my work. What I'm going to do is I'm going to try to factor my numerator and denominator and then try to simplify. That's what I want to do. So this is going to become x plus 3, x minus 2 when I factor it. My denominator, when I factor that, is going to be x minus 4, x minus 2. And also, I have made a mistake here that I'm going to correct, and that is that since I haven't evaluated the limit, I do want to carry over my limit here, right? This has to be the limit as x approaches 2 of this thing. Now what I will do is cancel the x minus 2 factors and then try to resubstitute. And when I resubstitute, I do get an answer. 2 plus 3 is 5. And 2 minus 4 is negative 2. So this answer is negative 5 halves. That is the limit of my function. All right, now what does this mean? Now this should not look like totally new to you, because at least in my class when we started this out, what we did was we were analyzing rational functions, right? And we realized that when you have a rational function like this one, and you want to determine its characteristics, such as its vertical asymptotes and horizontal asymptotes and intercepts and so forth, you want to factor both the numerator and denominator. And so when you factor, you realize that when you get a 0 in your denominator that gets canceled by a factor, an equivalent factor up in the numerator, that's the location of a hole. So I know right off the bat, as soon as these x minus 2's cancel, the characteristic that I have on the graph is a hole at x equals 2. Right? I have a removable discontinuity, or a hole, at x equals 2. And for the fact that I have x minus 4 in my denominator, that's a discontinuity that would be a vertical asymptote at x equals 4. Now, that's not important to us here because I'm evaluating at x equals 2, which is the location of the hole. So the bottom line is this. This limit that we have is the y location of the hole of that function. And that is then our limit. Okay. Getting a little dry there. Okay. Let's carry on. Now, I want to talk about the limit existence theorem. And this is telling us when will a general or two-sided limit exist. And here's the theorem. If you've worked with limits for some time, you know that this is true, but I'll show you the implications of this on a few problems. This says that the limit of f of x as x approaches c, right? Don't forget, that's a two-sided limit, right? We're not talking about a one-sided limit here. So a two-sided limit will exist if and only if that limit of f of x as x approaches c from the left is the same as the limit of f of x as x approaches c from the right, and they both are equal to the same number L, where L is a real number. All right, so you can't say that a two-sided limit is equal to infinity or negative infinity, right? It's going to exist if it is approaching a y value L. All right, so that's how we know a limit actually exists, because if two things could happen, either the left and right hand limits are not the same value, they both have a value, the left and right limits, but they're not the same value, then the two-sided limit at that x value doesn't exist. It's a D and E. Or maybe they both are the same, but they're infinity or negative infinity. But in that case, it's still the two-sided limit doesn't exist. So that means if you're evaluating a rational function and you're evaluating a limit at a location where you have a vertical asymptote, then the limit doesn't exist at that location, plain and simple. Now, I'll show you, I'll delve into this a little bit more on some specific examples. But let's kind of use that theorem to solve this limit, right? Where the limit the function that we're taking the limit of is a piecewise function. So I'm trying to find the limit of this function as x approaches 1. So what I have to do really is consider the two-sided limits. I have to consider the limit of g of x as x approaches 1 from the right, and I need to find the limit as x approaches 1 from the left of my function g of x. Okay, well, let's do that. Now, coming in from the right-hand side at 1 is going to be this function right here, right? Because this says this is the one that I use for x greater than 1 or higher than 1, or for our case, coming in from the right. So I'm going to evaluate this, right? This is going to be x cubed plus 1. That's what g of x is. I'm going to write it like this, class. I'm going to say the limit as x approaches 1 from the right of x cubed plus 1, because that is g of x when I am to the right of 1. And through direct substitution now, this becomes 2. Now I'm going to then say, okay, well, if I'm going to evaluate this limit as 1 comes in from the left, I would then be using this part of the function, because that is the piece of the function when I'm using numbers that are less than 1. So this would be x plus 1, and that is equal to 2. So that tells me that since the left-hand limit and the right-hand limit are the same value, yeah, the limit exists. So we could then say the limit as x approaches 1 of g of x is equal to 2. Therefore, if I'm working with a piecewise function and I'm evaluating the limit at the place where the two come together, and I happen to get a different number for the left and the right-hand limit, then that means the limit doesn't exist there. Okay, let's carry on. So let's go to the conjugate method. So as always, when we're presented with a limit, we're going to try direct substitution. That's our first attempt to evaluate the limit. And here, if I substitute this in, I'm going to get the square root of 3 plus 1 minus 2 over 3 minus 3. That's the square root of 4 minus 2. So that's 2 minus 2, or 0. So that's 0 over 0. So that's not going to work, right? And I'm not going to write equals 0 over 0, because that would not be a true statement. And if it's a free response question, your teacher will probably take a point off, and most certainly on the AP exam, on the free response, they would as well. So just keep that in mind. All right, so what we're going to do, it's a trick here. This is not really intuitive that like, hey, that's something that this thing I'm going to show you, the conjugate method, is something that you should try. It's not obvious. Once you see it, then you know. But what I'm going to try to do here is I'm going to multiply top and bottom of this function by the conjugate of the rational portion, right, of the rational part, which is the top part. So the conjugate would be root x plus 1 plus 2. And if I do that on the top, I need to multiply the bottom by that same binomial, like that. And because I don't want to change this function, right? Because basically, if I'm multiplying by this fraction here, I'm multiplying by 1. Now, what I'll do is execute that multiplication. This is a binomial. This is a binomial. And the great thing about multiplying two conjugate binomials is I know that the outer and inner products are going to cancel each other out. So I just need to multiply the two first terms and the two last terms. So root x plus 1 times root x plus 1 is just x plus 1. Negative 2 times a positive 2 is a negative 4. Down here, I'm really not going to multiply these together because I'm, as you'll see why in just a second, I'm just going to leave them as the product of those two binomials. But what happens then is that my numerator, this problem just so happens to be such that my numerator now is x minus 3. And here I have x minus 3 times root x plus 1. And then that is plus 2 down here like that. And what happens is, I think you can see it, right? This x minus 3 is going to cancel. It leaves me a 1 on top. And now I can go back and do direct substitution to evaluate this limit. So this would be 1 over the square root of 3 plus 1 plus 2. So that's 1 over square root of 4 plus 2. So that ends up being 1/4, like that. All right, now a few things about doing a free response question and you're evaluating a limit, right? Be sure that you bring your limit statement with you all the way while you're doing these simplifications, like in this case, the conjugate method, or if you are factoring and then canceling and then doing substitution. At every step, the limit comes along until the very point where you substitute that x value into the function. That's when the limit disappears. So notice I have the limit here, but then it's equal to, the limit's not here anymore. That's because I went ahead and I did direct substitution in for x. All right, let's keep it rolling. We're at about 9:30, so let's go to the next one. All right, this really is maybe a different method, right? This really doesn't fit into either of the ones that we're talking about, but this is really just kind of simplifying a complex fraction. But again, we try direct substitution. That's always the first thing that we are trying here. So through direct substitution, I get 1 over 0 plus 1 over 1/3 all over 0. So again, it looks like this, I can't really evaluate this. If the limit exists, doing direct substitution doesn't look like it's going to get the job done. So what I'm going to do is I'm going to try to get rid of the complexity in this complex fraction. And there's a couple of ways that we could do it. I'm going to do it this way. I'm going to multiply the top and bottom by the least common denominator of the fractions within my fraction that makes it complex. And those two denominators are x and x plus 3. So I'm going to multiply top and bottom by x plus 3. Like that. Right. And so this really has nothing to do with calculus or limits specifically. This is how we eliminate complexity in a complex fraction. Is multiply top and bottom by the least common denominator of the inner fractions. When I do this, bringing down my limit, right? Haven't evaluated the limit yet. I am going to take this whole thing, right, times each one of these fractions. And so what's that going to give me? Well, the x's here would cancel. This is going to give me an x plus 3. And when I multiply this by 1 over x plus 3, the x's cancel, and I am left with that. Okay. And now what I'm going to do is I'm going to multiply this over here. So x times, this would be x squared, I should say, x squared times x plus 3, like that. All right, so let's make sure that is what we want. So the x's cancel, we have x plus 3. Here the x plus 3's cancel, leaves me an x. And I'm multiplying there. I think that's going to work. Let's carry this on through. So this is the limit as x goes to 0. This is interesting. Limit of, that would combine to be 2x plus 3 over x squared times x plus 3. All right, so Now this, what is this giving me here? This gives me, through direct substitution, this is giving me a 3 on the top and a 0 on the bottom. Okay, so I think I want to come back to this one because I want to show you a technique before on another problem before we apply it to this one. Okay, so let's come back to this in just a second. All right, let's go down to this one. All right, now this one is sort of a unique one. This is the limit as h goes to 0 of this rational function. If I do direct substitution here, keep in mind, this is not as x goes to 0. So this is as h goes to 0. So this would be x plus 0 squared, or x squared, minus 3x, because h goes to 0, minus 3x. And then over here, distributing that minus, I get a minus 3x squared, minus x squared, and then a plus 3x, all over 0. Okay, so do you see that these all cancel out? I have 0 over 0 through direct substitution here. So what can we do? This ends up being 0 over 0 when h goes to 0. So what I'm going to do is I really only have one choice, and that's to expand everything that I have here and then simplify. So this would become x squared plus 2xh plus h squared. Distributing the minus 3, I get a minus 3x minus 3h. And then distributing that minus is a minus x squared plus 3x. This probably looks familiar to you. You might have done in pre-calculus something called the difference quotient, which is where this statement comes from. And we'll be using it in our class here very soon. Now, what happens here? In terms of simplification, right, the x squared and negative x squared go to 0, negative 3x and 3x, that's 0. So what I'm left with now is the limit as h goes to 0 of 2xh plus h squared minus 3h all over h. And you can see that h is a common factor in each of those three terms up in the numerator. So this becomes limit as h goes to 0 of 2x plus h minus 3. Now, as h goes to 0, remember, it's h, it's not x. So that would mean that this is 2x minus 3. And that's the answer to this. The limit as h goes to 0 is not numeric in this case, right? It is a function, 2x minus 3. I want to talk about next one is the special trig limits. And what I'm going to do for special trig limits is I'm going to use a limit that you may have seen in your class here. The limit of the function sine x over x as x goes to 0 is equal to the number 1. So that's something that I'm going to use to evaluate a few limits here. And kind of a corollary to this is also another one, that the limit as x goes to 0 of sine ax over ax, that's also equal to 1. Okay, so that is something else that we're going to use. So if a is a constant, then that's also equal to 1. So, okay, so what can we do? What I want to do is I'll use a property of limits here too to evaluate this, right? I have sine 3x. So what I'm looking at here is if that was a 3x right there, if that was a 3x, then then that limit would be equal to 1. So what I'm going to do is I'm going to make it a 3x. So here's what I would do. So I would multiply top and bottom by 3. And that's going to give me 3 times sine 3x, right? Because I'm basically coming in here and just saying, okay, let's multiply the top and the bottom by 3. And that's going to be 3 sine of 3x over 3x. I am going to move that 3 out to the front. That's one of the properties of limits, that if you have a constant multiplier inside your argument, you can take it to the outside and multiply it by the limit. So that becomes 3 limit of sine 3x over 3x as x goes to 0. Now, through substitution, I know what this is, right? This limit right here is 1. So that means that this is 3 times 1, or 3. Okay, so I'm kind of combining properties of limits with what we could call kind of a limit identity, right? I mean, that's just a statement that we know. We haven't really developed and haven't shown at all, why that's true, except to look at it graphically and to see that the limit is indeed 1 for that function sine x over x. All right, let's look at another one. So through direct substitution here, I do get 0 over 0. But I don't really have a way to factor or simplify, or the conjugate's not going to help me. So what I'm going to do is try to do a little bit of manipulation. And then I am seeing that I like this, sine x over x. So I'm going to go ahead and separate this into 2 separate fractions. Right? So I definitely can take the limit as x goes to 0 of x over x plus sine x over x. Just splitting that one fraction into 2 fractions by the common denominator. All right, so let's just develop this step by step. The argument of my limit here, x over x is 1, and that's still sine x over x. One of the properties of limits is that we can split limits apart by addition. We can do it by addition, subtraction, multiplication, division. I'm going to do it by addition here, right? So this is limit as x goes to 0 of 1 plus the limit as x goes to 0 of sine x over x. And that limit of sine x over x as x goes to 0, we already said, it's 1. So now this is also, it's a property of limits, right? But the function 1 is a horizontal line. And so it doesn't matter what the x value is. If you evaluate the limit of a horizontal line at an x value, it's going to be whatever the, that y value is, right? So this is a 1 and this is a 1. So this limit is 2. That is my answer to that problem. All right, let's try another one. See if we can make any heads or tails out of this one. Well, all right. So if we try direct substitution, again, it's 0 over 0. So, when you come across a problem that you're kind of like stumped on, you at least take a first step, right? Ask yourself, what is it that I could do in this scenario? Now, the only thing I really see is that denominator I could factor. So that's what I'm going to do. I'm going to factor out its greatest common factor. So this becomes sine x. I pull the x out, I get 3x minus 1. There we go. Now, see, this part right here is what I like, sine x over x, because I do know what the limit is of that as x approaches 0. And as I said, we can split limits out by multiplication or addition or subtraction or division. Here I'm going to split them out by multiplication. So I'm going to do this and say, well, I'm going to take out into one limit the sine x over x and then multiply that, right, by the limit as x goes to 0 of 1 over 3x minus 1. right? I can do that because I can consider this entire fraction that I have right here. I can consider that whole fraction. I can rewrite that as sine x over x times 1 over 3x minus 1. Those are equivalent. And so therefore, I'm just splitting it apart. This one is a 1. This one, by direct substitution, is a negative 1. Right? It'd be 1 over 0 minus 1. So that's a negative 1. I have 1 times negative 1, which makes that limit equal to negative 1. Next, let's try this one. Well, maybe we should try direct substitution right off the bat, which is what I am going to try. So I'm going to do 2 times sine pi over 3 squared plus 3 times sine pi over 3, okay, minus 2. And then down here is 2 times sine of pi over 3, and then a minus 1. All right, so what's sine of pi over 3? So, and there comes Alexa coming back on here. Okay. So sine of pi over 3, that's root 3 over 2. So let's see. Oh, I did direct substitution here, so I got rid of my limit, but let's see if this works. So this is going to be 2 times root 3 over 2 squared plus 3 times root 3 over 2 minus 2. Okay. This is 2 sine pi over 3. Sine of pi over 3. Yeah, root 3 over 2. So this would be 2 times root 3 over 2, and then minus 1. All right, so what does this give us? Let's see what we've got here. So this would be, that's 3/4, right? So this is 2 times 3/4 plus 3 root 3 over 2 minus 2 all over. This 2 times root 3 is root 3 minus 1. So that's 6/4 or 3/2 minus 3 root 3 over 2 minus 2 all over root 3 minus 1. All right, now let's see if there is a simpler way that this can be worked. So let me show you something here. Let's see. We want to go and take a look, right? I believe it's right here. So bear with me here. I'm going to get out my notes on this one. I think we're looking at something down here. No, I'm not sure. I wanted to show this as, oh, I see where I'm in the wrong section here. All right, let's go. Here we go. This is what we want. So let's try it. I think we want to go down to 1.5, maybe. Yeah, that's transcendental function. This, I think, is what I want. Let's see. Where is our function? Bear with me. I'm closing in on it, I believe. Yeah. Yeah. So, we can go ahead and simplify this and then rationalize it. Right, because the problem is I got a root 3 down in the bottom. So you can see that this ends up getting pretty messy through direct substitution. And I could have seen that maybe right off the bat that this thing wasn't going to give me 0 over 0. But, however, this thing still can be simplified. So let me show you what I'm going to do. All right, so I'm going to erase all of this work and see if I can maybe simplify this before I do the direct substitution. And you've got experience in this because you've done this in pre-calculus in terms of simplifying trig functions, right? This was part of your trigonometry section, trig identities. But now what I do recognize is that my numerator can be factored, right? It's a quadratic type expression. So that means then, because this is a squared sign and this is a power 1 sign. So I'm going to factor this as 2 sine x and a sine x, like this. And I'll leave this as 2 sine x minus 1. And I need my products of these last two terms to be negative 2. So if I put this as a negative 2 and a positive 1, then my out product is that's a negative 4, and my inner is a positive 1. That would give me a negative 3, but I want a positive 3. So I'm going to change that. So this is going to change around, and I'm going to make this a minus and this a plus. Now my outer product is 4 sine x. My inner product is negative sine x. That combines to be the positive 3x. So I have factored this properly. What this allows me to do is to cancel those two terms. Now this is much easier through direct substitution. This becomes sine of pi over 3 plus 2. I know that pi over 3, sine of pi over 3 is root 3 over 2 plus 2. And that's my most simple pathway to get to my answer through direct substitution. And one-sided limits. So here, I want to show you these two problems here, class. So we're kind of in the bonus thing here. We've got, we still got about 10 minutes left here. So what I want to show you here is how would I evaluate these one-sided limits from for the right and the left. And here's the thing that's happening. If you do direct substitution, you do get 0 over 0, right? And in fact, when I look at this, I realize that my function doesn't exist at x equals 4 because I get 16 minus 24 plus 8. My denominator is 0. So that means that if this was a two-sided limit, if they had asked me for this function, what's the limit as x approaches 4, by the limit existence theorem, the limit doesn't exist. Because if there's a vertical asymptote, if there's a vertical asymptote, the limit is not going to exist there. Now, if I write this in factored form, and if I just consider what this is, being x plus 3, x minus 2, and this being x minus 4, x minus 2, right? We've already looked at this and we realized that, there's a hole at x equals 2, and then there's a vertical asymptote at x equals 4. So that would tell me right there that the two-sided limit, the limit of this function as x is 4, does not exist. However, they're not asking me for the two-sided limit. They're asking me for the one-sided limits on either side. And I know that if I have a rational function that has a vertical asymptote at 4, from the right and left, the function is either going to be going up towards it or down towards it, not both, right? It's either one of those. And from the right, the same, right? It could be going up or it could be approaching it down towards and then heading towards negative infinity. So that's what our job is on a one-sided limit like this, where there's a vertical asymptote, we got to figure out, hey, is this thing a positive infinity or a negative infinity? So let me show you a trick on how we're going to do that. So what I'm going to do is I am going to just formally write this out by writing it in its factored form. So it's going to look like this on the top. The bottom is x minus 4 times x minus 2. All right, now these, I'm going to go ahead and remove the x minus 2's. Now what I'm going to do is this. I'm going to say, well, I know that my denominator is going to be 0 if I'm right at 4. But coming from the right at 4 would mean I'm going to use a value just to the right of 4, which would be 4.1. And what I'm going to do is I'm going to evaluate x plus 3 over x minus 4 at that value that's just to the right of 4. And I don't really care what the number is, right? I just care whether it's positive or negative. So what's that is going to yield is it's going to yield a positive number on the top, right? 4.1 plus 3. And then the bottom, it's going to be 4.1 minus 4. So if I'm to the right of 4, this denominator is always going to be positive. And a positive divided by a positive is a positive. So this one-sided limit is heading to infinity. That's how that's going to work. Over here, this one, same analysis, right? So this ends up being the limit as x goes 4 and coming in from the left. And I've got the x plus 3, x minus 2. I have x minus 4, x minus 2. These are canceling. I'm now going to let x be a number that's just to the left of 4, which would be 3.9. And then I'm going to consider what would my numerator be. It's going to be positive. But 3.9 minus 4 is a negative. So that means that this answer is going to be a really large negative number, because the closer I am to 4, the smaller that's going to be in the denominator. So it's going to cause it to get bigger and bigger, but it's going to get bigger and bigger in terms of going towards negative infinity. So my answer here is a negative infinity. So bottom line is this. When you're evaluating a limit through direct substitution, if you get 0 over 0, when you get 0 over 0, what you're going to do is you're going to try to either factor, simplify, and resubstitute. You might use a conjugate method. That may be something that you could try. But 0 over 0 means you have more work to do, more simplification to do to figure out what the actual answer is. But if you get an answer that's not 0 over 0, but like 4 over 0, then you know that there's going to be a vertical asymptote at that location. And so what you want to do is use this trick, right? So I know at this 4, I got the vertical asymptote. So let me just choose a number just to the right or just to the left, whichever one-side limit you're working, and then figure out whether the resulting answer is going to be a positive or a negative. All right, so that's going to be the trick on that. That means then that if we went up to this problem that I had skipped, yeah, this one where I tried evaluating this by multiplying top and bottom, by removing the complexity, I ended up with this, which gave me a 3 over 0. All right, now let me take a quick look here because I want to find out what our answer is here before I go too much further. And it is 2. Let's see what happened here. I'm looking for. I am looking for a particular problem. Let's see if I can see where it is. Well, it's here somewhere. Let's see. Having a hard time locating it. But at any rate, if I were to evaluate this, I have a vertical asymptote at x equals 0. All right, so you can see that. And because I have a discontinuity at x equals 0, and it's not getting removed by any factor up in the top. So what I can do in that case is say, well, I am going to evaluate this. I'm going to let x. Oh, okay. So hold on. So if that's true, see, if I have a vertical asymptote, I already know what the two-sided limit is, right? This is a general two-sided limit. The limit does not exist. That's why I was trying to see if maybe I wrote this and copied this problem down wrong. Let me take one more look at this, class, and see, because I had worked this out previously, and I just, for some reason, I can't find it in my notes here. It's here. It's here somewhere. Let's try one more shot through here. So let's go back up to my original problem. Yeah, that's the one that I'm looking for. Okay. I found it. Yeah. So this ends up being a DNE. Okay, it's a DNE. Now, just for the sake of, because remember what I said, if there's a vertical asymptote at the place where you're evaluating that limit, the two-sided limit doesn't exist. But suppose that they had asked, what's the limit as x approaches 0 from the right-hand side of this function. Let's just change it a little bit and make that the problem. So what you want to do, since you know there's a vertical asymptote at x equals 0, we're trying to find out, is the one-sided limit, is it infinity or is it negative infinity? So we'll let x equal 0.1, which is right to the right of 0. Now, what will that yield in terms of my function? Well, that's going to give me a positive on the top, right? 2 times 0.1 plus 3. That's a positive answer. This is going to be positive. X squared, 0.1 squared. That's a positive, very small positive number. And time positive. That yields a positive answer. So I know the behavior of the function now, where I've got the vertical asymptote right here. Coming in from the right-hand side to 0, it has to be going up towards positive infinity, not down towards negative infinity. If we, excuse me, if we also let this be, if we wanted to evaluate the left side limit, right? If I wanted to change this and say, hey, let's evaluate it coming in from the left-hand side, then I would say, well, let's evaluate at a negative 0.1. Just to the left of 0 would be a negative 0.1. And that is going to give me still a positive value up here, right? That's going to be a negative 0.2 plus 3, positive. My negative 0.1, when I square it, will turn it positive, and a negative 0.1 plugged in right here, still going to be positive. So I kind of know the behavior of the function as it approaches that vertical asymptote by using one-sided limits. All right, I think it's 10 o'clock. We've gone an hour. I think I'm going to cut it off there. I had a few other problems, I think, on the one-sided limits, but maybe we'll pick those up next week. So if you are watching this on the replay, if you found any value in this and you've made it this far into the video, please go ahead and hit a like for me and subscribe to the channel, and you'll get notified when I have more live streams. If you are interested, I am doing tomorrow night a live stream where I'm going to be doing an SAT practice test from start to finish, where I think out loud, so you can see my process and my techniques in trying to get a perfect score. Okay, that's it, class. Thanks for joining, and I will see you next week at 9 o'clock here on my YouTube channel.